Howie had a good idea that I'll go ahead and record it just in case. Um, so if you've done any logic synthesis like in logic design, good morning, more alarm clocks for you too, I think. So I think the class goes 10 minutes longer now, right? Except for Howie, who gets to leave early. So he gets definitely the points for participation from you guys. So, all right. So in logic design, you know, the first step is to come up with a two-level logic implementation. But normally you can't actually implement a two-level sum of products implementation in a real technology directly. The reason for this is that AND and OR gates of arbitrarily large fan-in are not practical. You can't typically have a gate with more than 3 or 4 inputs, for example, in CMOS. So when we build a two-level logic function for a complex system, you might have 10, 20 input ANDs and OR gates, and obviously you can't find those in any logic family. So two-level sum of products implementations have to be decomposed to fit into logic gates that you actually have in your library. So this means that you need to apply laws of Boolean algebra to derive multi-level implementations. But we went through all this effort that we talked about last time to make sure that there were no hazards in our two-level implementation. So it'd be a shame if through the decomposition that we ended up with hazards. So we have to be very careful that as we go from two-level to multi-level, that we don't take our hazard-free implementation and start putting hazards into it. So fortunately, there's a number of the laws of Boolean algebra that are hazard-preserving. And what that means is that if you take a logic circuit and you apply this law of Boolean algebra, any hazards that were there before are the same hazards you have after. Or in our case, if you have no hazards before, you have no hazards after. So it will not introduce any new hazards to your circuit. So if we begin with a hazard-free sum of products implementation and only apply hazard-preserving transformations, then the resulting multi-level implementation is also hazard-free. So in 1969, Unger proved these laws were hazard-preserving. Namely, for any expression f1, if we transform it into another expression f2 using these laws of Boolean algebra, then hazards will be preserved. So for example, if you apply the associative law, which is basically decomposition of an OR gate, right? So if you break this 3-input OR gate, for example, into two 2-input OR gates like so, that preserves hazards. Or similarly, if you go the other direction, it's also preserving hazards. So you can this means you can kind of arbitrarily associate your function, which is essentially decomposing a large function. The same goes for products. If you have, say, a 3-input product and you decompose it to two 2-input products like so, you are not going to introduce any hazards, which is good also if you have an arbitrarily large product. The De Morgan's theorem, which hopefully you remember from your logic design classes, is also hazard preserving in both directions. So you can convert ANDs to ORs with the appropriate complements. So this is taking, I guess, a NOR, converting it to inverted inputs in an AND. And similarly, if you take a NAND and convert it into an OR with inverted inputs, or vice versa in both of these cases, you can basically exchange the gate complementing as you go, and that's also hazard preserving. The distributive law, where you factor out a signal, is hazard preserving, but the reverse is not hazard preserving. So if you want to multiply through, you might actually introduce hazards, and so you can only apply this law in this direction. But that's actually typically the direction you'd want to apply when you're doing synthesis, because it's the one that ends up with less literals when you're factoring. The absorptive law that says if you have A or A and B and you reduce that to A is hazard preserving. But the reverse is not hazard preserving if you try to introduce this term. And then finally, the last one here, which takes A or A not B and reduces it to A or B, is hazard preserving, but the reverse is not. So in all of these cases, it looks good because the circuit, if it starts with no hazards and you apply these laws, you end up with no hazards. And the laws all seem to be taking you in directions that you would think that you'd want to go towards simpler logic. That's all good, except for an arbitrary multi-level logic synthesis engine sometimes takes backward steps. It's sometimes advantageous to actually add complexity temporarily to your circuit, and then it simplifies more later. So sometimes you might actually want to do something like that. It doesn't seem like it doesn't seem clear why you would want to do that. But the multi-level synthesis engines, they actually sort of going along your landscape, climbing hills sometimes by adding a little complexity that then help to simplify something else out along the way. So you have to put some constraints on your logic synthesis engine. Another thing that something like a multi-level logic synthesis engine will do is it'll do minimization as it goes. It'll try to do logic minimization. And you also have to shut that off. Because why would minimization be a problem if it tried to simplify your formula?
The gate might become complex.
So when we made something hazard-free, what did we tend to do? What did we tend to add to the circuit?
More states.
Not more states.
More encoding bits for states.
No, I'm talking about for hazard-free logic synthesis. Were our covers as small as they were for conventional synchronous design? Or did we had to add prime implicants, or even add non-prime implicants to get to a hazard-free cover? So those to a simplifier are going to look redundant. So these supposedly redundant products that we've added to eliminate hazards, to cover hazards, they're going to get eliminated by a simplifier. Because the simplifier is going to go, oh, I've got some other product that covers it, not realizing that product is in there to cover a static hazard. Does that make sense? So we have to put some shackles on a multi-level synthesis engine and tell it, I've put that logic in there for a reason. Don't simplify it out. Basically, you can't let it do the simplification.
But applying any of these laws might simplify, right?
These are...
the absorptive law can...
The absorptive law is simplifying it.
Yeah.
That's true. But it's not going to remove the redundancy that we've added for hazard freedom. So this is not a... this is simply just a prime... this is like this is a smaller cube than that one, right? So that cube is okay because it's already there. And then that cube is just extra, it's going to be a subcube within that cube. So eliminating it's not going to cause you any problems in that case. But it's a good point, is that some simplifications are okay, but simplifications where you say, oh, I've got this product, it covers some minterms of this product, and then you go, okay, well, I don't need that product because it's only covering redundant minterms. That's not okay because we added that product to remove a hazard. The second thing is there are hazard-preserving hazard exchanges that you can do. So for example, the insertion of a deletion of inverters at the output of a circuit only swaps 0 and 1 hazards. So if you took a circuit and you put an inverter at the output and you used to have a static 1 hazard, you now have a static 0 hazard. Insertion or deletion inverters at the inputs only relocates the hazard to the duals of the original transition. So it's just going to move the hazard somewhere else in your function. And the dual of a circuit, basically, if you exchange all the AND gates for OR gates, is just going to produce dual hazards. So it's just going to move the hazards around. So again, you can do, if you had no hazards and you apply any of these rules, you'll still have no hazards. But it's just basically saying that, okay, so when I say have no hazards, one important fact there is that remember, if you think about a logic function in any possible multiple input change, there's hazards. The only reason we could get a hazard-free implementation is we restricted ourselves to only the transitions that really happen in the burst mode state machine. Only those transitions do we eliminate the hazard for, right? So if you drew any random transition into a Karnaugh map, you might have a function hazard or something like that, but those would not be the burst mode hazards that you're eliminating. So all functions have hazards under some multiple input change.
So when you say preserving, it means that, let's say if one of the function had a data hazard, so it will still be retained, but this will not introduce any new hazard. But if it didn't have any hazard, then this will not introduce any new hazard.
Right. So first of all, logic hazard, not data hazard. Data hazard is a computer architecture term. But yes, so every function will have hazards, but the hazards that you see are not necessarily hazards that you care about because they're not transitions in your burst mode machine. So what you do when you do hazard-free logic synthesis is you eliminate the hazards that can happen due to transitions you actually could see in your machine. You eliminate all those hazards, all the ones that we find when we take the flow table, remember, find all those transitions that we need to make hazard-free. You make all those transitions hazard-free, you're happy. So those transitions are hazard-free in your 2-level, they'll be hazard-free in your multi-level if you apply only the rules that we said are hazard-preserving. So any of the hazards that you didn't care about because they're never going to happen, you never have inputs like that would cause them to show up, they're still there, that's fine. But the hazards you eliminated by your logic synthesis, they're still eliminated. Does that make sense? So here's an example. This is actually the example we derived earlier for the burst mode example I did earlier. And we have a 5-input OR gate, and there aren't any families of 5-input OR gates. So we want to optimize this. So we can do things like apply the distributive law, because it's hazard preserving. So in the distributive law, you can see that I factored out C prime out of the first 3 terms. Or sorry, I factored out C prime out of this term, and this term, and factored out C out of those 2 terms. And that decomposed the function, just applying the distributive law. So now I don't have any 5-input AND gates. And this one, because it was hazard-free for the transitions I cared about, it's still hazard-free for the transitions I care about. Does that make sense? So in general, so multi-level logic synthesis is the subject of almost an entire other class that Priyankala teaches on logic synthesis. So I'm just giving you a sampling, just explaining to you that multi-level logic synthesis technique can be applied, but it just has to be slightly constrained. So that was a whirlwind in a multi-level logic synthesis. Now the next step of logic design is technology mapping. So in this case, when we decomposed it to ANDs and inverters, they're still technology independent, right? These are just logic functions. I haven't said, whether you're building them with CMOS, whether you're building them with, bipolar or genetic gates or whatever, right? I'm just saying that you've got an implementation in sort of a technology independent form. Technology mapping is a step where you take your technology-independent logic equation and you map it to a library of cells in a gate library to produce a net list of cells, right? So ultimately, you have a library of gates and you want to select the minimum area or minimum selection of gates that will give you a minimum area or minimum delay for your logic function, okay? That's technology mapping. So technology mapping is usually broken down into 3 steps: decomposition, partitioning, and matching and covering. So decomposition transforms the logic equations into an equivalent network using only 2 input, 1 output base functions. So in order to figure out how to map your function, it's convenient to put your logic into sort of a canonical form. So you take your logic and you're going to break it down into only 2 input NAND gates, for example. Well, decomposition performs recursive applications of De Morgan's theorem and the associative law. And as I explained earlier, those are both hazard-preserving transformations. So simplification. So as long as you don't simplify any redundant logic as you're doing this, then you are going to have the hazard-free properties that you had before. So again, as I mentioned, you can't do any simplification as you're doing the decomposition. You just you need to leave the redundancy in that you put in for hazard coverage. But otherwise, you can just decompose it as you go before. So let's say this is our output of multi-level logic synthesis, and I need to break that into NAND gates. Okay. So you can just use De Morgan's theorem and associative law to turn this into NAND gates. So using the associative law, I'm going to take, this is a 3-input gate, but I only have 2-input NAND gates in my base functions. So I need to turn that into a 2-input gate, and I use the associative law to turn that into two input gates. Then I can apply De Morgan's theorem to turn that into a NAND gate. So I flip that using De Morgan's theorem. And then I can do De Morgan's theorem again because I need to change that OR gate into a NAND gate. And I also did the same on this side, of applied De Morgan's theorem to turn that OR gate into a NAND gate. And then a De Morgan's theorem over the entire thing to get rid of that OR gate. And that's this function here. So this is logically equivalent to the function before, but it's only using 2-input NAND gates and inverters. You see what I did? So you just apply associative law to get rid of get all gates down to 2, and then you apply De Morgan's theorem to turn all your ORs into ANDs. And then this is logically equivalent to the function I showed before. Okay? But it's in a sort of a canonical representation that makes it easier to do technology mapping. The next step is partitioning. And partitioning, what it does is it takes any multi-output function and it breaks it down into single output cones of logic. It's sort of a divide and conquer approach. So since partitioning doesn't change the topology of the network, it doesn't affect the hazard behavior. So partitioning is completely legal as well. And then the last step is called matching and covering. So matching and covering examines each cone of logic and then finds cells in the library to implement subnetworks. And this matching and covering can be done in 2 different ways. One is called structural pattern matching, which is where you find logic gates have the same logic structure when decomposed into 2-input NANDs and inverters as the subnetwork you're looking at. And then Boolean matching techniques consider the actual Boolean functions of the subnetworks and compare them and see if they're the same. So in the structural techniques, each library element gets decomposed into base functions the same way that we decomposed the function we're trying to implement. Then the library elements are compared against portions of the network doing pattern matching. And then assuming the decomposed logic and library gates are hazard-free, then the resulting map logic will also be hazard-free. So here is a library of a whopping 6-gate library. And you break it down into 2-input NANDs and inverters. So an inverter, of course, is already broken down, and I'm going to say it has cost 1. 2-input NAND, I gave cost 3. 3-input NAND, this is a 3-input NAND, but shown using only 2-input NANDs and inverters, so it's broken down into base functions. We'll call that cost 5. A 2-input NOR is the same as having a NAND with inversions on the inputs and the outputs. And or invert 1 block is and or invert where you have an and with a 1-input inverted. And so this logic function we'll say is cost 3. And then this is an and or invert 2 that has 2-input ands ORed together. And we'll say that that has cost 4. Okay? So these are not actually how they're implemented, but they just show you them in equivalent form using NANDs and inverters. Does that make sense? Okay. So now this is my library, and this is my subject graph that I'm trying to cover. And then what I do is I start walking up the network, and I think this is not going to go in the video very well, but so be it. They didn't show up to class. So what you do is you start walking up this network covering subtrees. And so you see at this point, I could say I can cover this guy with cost 1, that inverter right there. I can cover this guy with cost 1. Okay. Then this NAND gate, I can cover it with this cost 3, which is actually cost 5, because it's 3 plus 1 plus 1. Okay. And then when I get to this one, I can put another inverter on, which gives me 6. But notice this. 2. This also could be done that way, right? So instead, I can do it like that for cost 2, and that's the one I'm actually going to be happy with. So then I have to keep working up my tree. This is cost 1. This one is another NAND. So it has cost 6 plus 3, which is 7. And did that cover anything?
Should we do 6 plus 1, or is it like 2 plus 1 plus? Because you already did.
Oh, sorry. What did I do? Yeah, I added wrong, right? So it's 6 plus 3, which is 9.
Yeah, so no.
I haven't counted this guy in. I'll count him in later.
No. The one before that. So we already said that that can be implemented as a 2. So should we?
Oh, sorry, 2, right. Yeah, sorry. I'm looking at my wrong numbers. Thank you. 2 plus 3, so this should be 5, right? But I also have the option of covering this guy with that one, which has cost 5 plus 1 plus 1, which is 7.
Yeah.
Right? So I actually have 2 choices. I can either do these 2, which has cost 5, or I can do this, because that matches that, which has cost 5 plus 1 plus 1, which gives you 7. But this is the best one, so that's the one I keep. Okay? Now I move up to this one, and I see, okay, that has cost 3, 5, 8, 9. But that also matches this one, which is 3
plus 2,
which gives me
5.
And then I can go up this way. That's a cost 3. These 2 together is going to be still 6. These 3 together, I don't think there's anything I can do about that.
So
9. And then I have to take this one.
Those 3 can be covered under 4.
Right, so we have lots of choices here, right? So I can take this one, which would be 3 plus 5 plus 9,
So
17. Or I could take this one, right? That's 4
plus 6.
6 is 10
Plus 6.
plus 6. 4 plus 6 plus 6 is 16, right?
Yeah.
So that's better. So if that's my final one, then I'm going to have an AND OR invert here, and then I'm going to have that be 2 NANDs. That'll be inverter, that'll be inverter, and that will be the 2-input NOR. Let's see if I don't think that's right.
So AOI 1, yeah.
Yeah, I think this solution here is wrong. I think this should have an AOI at the output. I only substituted out the NOR partially. So let's take this one, which is basically going to be, you'd have the
We didn't consider AOI 1.
AOI 1. Where could we consider AOI 1? We considered it here. I think that's the only place we can consider it. So I think we have an AOI 2, and then we have a NAND. Actually, the way you draw AOI 2 is like, that's a NAND, an inverter, and then this is a 2-input NOR.
Yeah, that's a NOR. NOR goes.
Yeah, oh, sorry, NOR goes to the second input.
Second.
And then this down here is going to be, that's fine. And then this one has,
2 NAND.
oh, this goes around to the beginning there, and then this one goes down to a NAND. Okay, so that's technology mapping. So this is using real library gates now. Okay, and again, technology mapping is a big subject of the logic synthesis class, and that would be hazard free. So I started, remember, with my original 2-level implementation, and then I derived a multi-level implementation, and then I did technology mapping, and all along the process, I was very careful not to introduce hazards. So I had no hazards. I eliminated the hazards in the 2-level step, and I just was careful not to introduce them as I went through the multi-level step. So one of the nice things about burst mode design is that in burst mode, in extended burst mode design, we're almost using synchronous synthesis. And that's really handy because we don't need to like use special logic synthesis algorithms for technology mapping. And as we'll see when we get to Moeller circuits are not as privileged when it comes to that. So that was structural matching. So in structural matching, you try to match the structure. There's another type of technology mapping called Boolean matching. And in Boolean matching, you try to match the logic function. So here's, this is another logic implementation. I think this is the GC one from before. And this logic function is implemented this way. So this has been done because this didn't get extended because there was a dynamic hazard intersection problem. So you've got a dynamic 1 to 0 transition there. And if you extended that like so, what you'd end up with is you'd intersect that dynamic transition without intersecting the start point. So because of that we shrunk this down. So in Boolean matching, you might look in your library, oh, I've got this 2-input mux. And this 2-input mux implements the exact same logic function as this one. But this is actually the way it's represented in the logically in the Karnaugh map, and so there's actually going to be that dynamic hazard possibility within that 2-input mux. So another researcher who worked on asynchronous design basically said that you have to analyze each of your library gates, enumerate what their hazard properties are, and then when you're doing comparing which gates you choose in Boolean matching, you need to make sure that the hazard properties of the function you're trying to implement are identical to the hazard properties of the function you try to replace it with. And if they're not, then you have to exclude that gate from your options. Okay. So assuming that I guess I already said that we have a dynamic 1 to 0 transition, the multiplexer has a dynamic 1 to 0 hazard. So you look at the transitions that you had when you mapped it, and you check to see whether those hazards exist in your library gates, and if they do, you have to exclude that library gate. So if this was the original implementation, the multiplexer would be okay. So if this was what you started with, you could use the multiplexer, but because this is what you actually want to implement, the multiplexer is not safe. Okay, so there's one last type of logic family I wanted to talk about, which are called generalized C elements. So generalized C elements are an interesting logic family because, I mean, they're based on the idea of a C element, which we heard about in chapter 1, but they're generalized in the fact that they're complex CMOS implementations of the set and reset logic for the C element. And the reason they're interesting is they can provide very fast and compact logic, and they can often be substantially faster and smaller than using conventional off-the-shelf ands and ors and things like that. So there has been some research that has demonstrated that there's a significant area performance advantage to using these. And assuming that you have some, for example, some software tools like Cadence or whatever may provide auto layout tools that can build arbitrary gates for you, then you could potentially build the gates on the fly as you need them. Or if you're doing custom design, for example. So what is a generalized C element? So remember, a C element, the logic function for a C element is when both inputs are high, the output is high. When both inputs are low, the output is low. But I've got an inverter there. So it's actually, when this is high and this is low, this goes high. When this is high and this is low, that goes low. And if these are both 0 or both 1, the value retains its old state. So it's basically kind of a set reset latch in a sense out here. And then this combinational logic represents a set function, and this combinational logic represents the reset function for you. So you can implement this logic gate here, shown complex and shown as basic logic gates, in CMOS like so. So you have basically your set functions that are implemented in NMOS transistors. So when, for example, if I want to implement that AND gate, is when that switch is on and that switch is on, I'm going to have ground coming up through here. That gets inverted to become a 1, and so this turns on. Or if this AND gate is on, this pair of transistors is on, that will also set the function to 1. if the complements of these two signals, they get complement because in PMOS you've got a complementation. So if these are both off, that pulls this high, which pulls the output low. Or if these are both off, then that pulls that high. And then if none of these stacks are switched on, then you have this little weak feedback here that restores the state here and keeps it at its stable value. Does this make sense? Have you guys had VLSI?
Yeah.
Okay. So you know what a transistor is and stuff like that. Okay, good. All right, so you can also implement this a little bit more. If you don't like weak feedback inverters, so weak feedback inverters are going to create basically a conflict here, right? Because the weak feedback inverter is going to need to be overpowered by these transistors when you're turning on or turning off the function. And so basically it's usually built with transistors that are maybe too long or something like that, so they're not very strong. If you don't like the idea of weak feedback because it sort of uses some power and you have a conflict, you can also build it by taking the dual functions of these. So this basically is take this function and this is the dual of it, such that this, when you need to turn this, when you need to push this low, this will actually be off, and so it won't drive it at that time. Okay? And similarly for this one, it's the dual of that function. Of course, that means more transistors. Okay, so generalized C elements, as you can see, this is a lot of logic smashed into a small number of transistors. And the other nice thing about it is generalized C elements have simpler hazard properties than two-level logic. So in particular, static hazards cannot manifest at the output of a GC gate because you have this sort of state holding capability that retains its state when you're moving from one stack to another, because that's, remember, where static hazards happened, is you'd have one product was turning off and the other one was turning on, and the one that was turning off turns off too fast. That's like one stack is turning off and the other is turning on. But because it's not really the stack's job right now to hold it, it's the weak feedback to hold it, there's going to be no static hazards. So GC gates have absolutely no static hazards. The one thing you do have is you need to avoid short circuit current. So short circuit current is where you have basically a path from VDD to ground, and that can heat up your chip and cause other problems. You don't want to have direct paths from VDD to ground, so you need to try to make sure that you don't actually have prolonged periods of time where both your pull up and pull down are on simultaneously. To avoid that, you need to be very careful about decomposing trigger signals, which during the transition both enable and disable a P and N stack. So if you have a signal that's going into both of these, top and bottom, that means that when that signal's flipping, it's turning one transistor on down here and one off down here, or vice versa. You want to be careful you don't sort of pull that logic out so you have unequal paths going to the two transistors. So by avoiding short circuit currents, product terms intersecting a dynamic transition no longer must include the start subcube. And the problems with conditionals and dynamic hazards are also not present in GC implementation. So you remember those slides that I felt like great pain showing you about how you have to worry about state minimization problems and the state assignment where you have to deal with those conditionals. Those hazards all go away with GC circuits as well. So you don't have to worry about those problems. So what do you need to worry about? So the hazard-free cover requirements for the set function in an extended burst mode GC are as follows. Namely, each set cube of your set function should not include offset terms, which makes sense. You're trying to set it, so your set cube shouldn't be on and your offset. For every dynamic 0 to 1 transition, you have a transition cube C1, C2 in F set. The N cube, C2, must be covered by some product term. So this is essentially saying that that C2 is a required cube, which it is in conventional. And then finally, any product of F set intersecting C2 of the 0 to 1 transition must also contain the N subcube. So in other words, you don't want to have a stack that is turning on and off during the transition because that could create a dynamic hazard. And then the hazard freedom requirements for F reset are just the dual of that. So when you're building F reset, they must not include onset min terms. For every 1 to 0 transition. In F reset, the start subcube must be covered by some product cube term, and any product, or sorry, every 0 1 0 transition, it's actually the n subcube must be covered by some product term, because now the n subcube is you're setting it to 0, right? So it's actually exactly the same like 0 to 1, but because you're setting it to 0, that the n subcube, which is the 0, needs to be covered by some product term, right? So you have to cover the 0 in that case, because it's like covering zeros when you're doing a dual function. And then, yeah.
The way we are putting this is like given any function, we decide its onset, offset, and give it to a C element as a set and reset.
Right. So the difference is that we discover what are the minterms where we're turning us from 0 to 1. So we're only looking at 0 to 1 transition cubes and 1 to 0 transition cubes. For 0 to 1 transition cubes, we have to add some transistor stack, which turns on monotonically during that 0 to 1 transition, and make sure no other stack will turn on non-monotonically while that one's turning on. For the offset, that's for every 1 to 0 transition, we have to make sure there's some product in the term that turns on in the n cube of a 1 to 0, because it's supposed to turn on to reset the function. So what we're basically doing is we're covering 0 to 1 transitions with with pull downs because of the inversion and in the NMOS tree, and we're covering the 1 to 0s in the PMOS. So we're covering just the dynamic portions because the static portions are handled by the keeper. Does that make sense? So we'll see an example. This should help.
And for the static portion, for it to hold, we are adding, because we considered inverter as weak, we added again the CMOS logic, right? So that the hold is stronger.
Right. So there's going to be this weak, this inverter is weak to hold. That can be overpowered by these transistors. So here's an example that illustrates how this works. So the first transition cube I'm worrying about is the 0 to 1 transition, and that is 0, 0, 0, A, B, D. So that's this corner, and I'm going from here to here like so. And that's a 0 to 1 transition. The required cube for that is this cube right here, where I'm ending. So that has to be in my onset. The privilege cube is this whole cube, not A. And then the end subcube is that minterm there, 0, 1, 0, 1. It's these two minterms here, because we're assuming that C is a directed don't care falling. This is the same example that I showed last time. And E is a level signal that's changing. Then I also have a 1 to 1 transition, which I think is this one, here to here. 1, 1, 0, 0, 1, 0 to there. So that's a 1 to 1 transition. The required cube, this one, is this cube, although it's not actually necessary in the GC implementation, because it's going to be held by the keeper. And then we also have a 1 to 0 transition, which is starting in this cube and going up this way, I think, if I'm remembering. Yeah. A, B, not D, which is here, A, B, not D, these two ones. And then it's going to, yeah, so it's going from these 4 to these 4. And so this is my required cube for this one. But as we'll see later, this is not the required cube in GC. But this was the required cube previously. And then this was the privilege cube. And then we had to worry about the start subcube, which was 1, 0, 0, 1. So it's this part here, assuming that C was a directed don't care that was rising in this case. But in generalized C elements, we'd only have to consider the two dynamic transitions. So we're going to skip this dynamic transition, or this static transition. We only worry about these two dynamic transitions. Now, the required cube for the set is going to be that one right there. And the required cube for the reset is going to be that one right there. Because when we go up there, that's when we want to reset.
No, the below one, right? All ones.
No, because it's when you get there, you reset. Because we're doing reset function. So this one is going to be part of the set function, and this one's going to be part of the reset function. So you can see that A prime BD, which is the required cube here, is actually implemented as my set A prime BD. Now the reset is going to be A not B not D, and that's A not B not D. That's those four right there. So that's where I want to reset, and then I put those in the PMOS stack, remembering that A is actually A barred because these have inversions there. And so this implementation implements that function precisely hazard-free. That makes sense? So you can see it's much more compact, but most gate libraries don't have these in their gate libraries. So that's the downside, right? Is that you're going to either have to custom design it yourself, or you're going to need to use some auto layout tool to try to build these gates for you. But the advantage, it's smaller and faster. So the last topic of this lecture is sequential hazards. So in sequential hazards, Huffman circuits require the outputs and state variables to stabilize before either new inputs arrive or fedback state variables arrive, right? So basically at this point, we've built our logic for our next state and output variables. We did our state minimization, we did our state assignment, built our hazard-free logic. We've mapped it, generalized C elements or standard logic. But the last thing to remember is that we have to make sure that the fedback state variables don't come around too quickly. We have to put delay in the feedback path, and that's what this part is about. The last step is to make sure that your feedback paths are the right speed. So Huffman circuits require the outputs and state variables to stabilize before any new inputs or fedback state variables arrive. So a violation of this assumption results in something called a sequential hazard. And the presence of a sequential hazard is dependent upon the timing of the environment, the circuit, and your feedback delays. So in this example, you imagine that you have an input X that switches from 0 to 1. Right? So if it switches from 0 to 1, then what happens is you're supposed to go over to this column and then get excited to go down to this state. And then what's supposed to happen is I get a 1 to 0 and I get excited to move over here, and then I move down to that state. Now the problem is if you feedback your state variables too soon. So think about it this way. So you have two pieces of logic. One which is trying to compute next state, which is state 2. And one which is trying to drive your output low. Okay? So what you're trying to do is you're trying to drive your output low. When X goes high, you're trying to drive your output low, and you're trying to drive to your next state. But what happens, let's say that you jump to your next state fast before your output even goes low, because you fed back the signal immediately. And then what will happen is you're going to find yourself in state 2, and maybe the logic for the output is still feeling the original 0, but it hadn't had time to stabilize. So it's going to potentially then output a 1 momentarily when it's supposed to actually output a 0, because it gets excited to output a 1 because that's raced in. If the input changes again too fast on it, it's going to output a 1 momentarily. So what we need to make sure is that there's enough delay in the feedback that you don't actually have the state variables change, feedback and change, and actually have you move down a row till the output's stabilized. Because otherwise you could have glitching on the output, these sequential hazards. You could also even have if the next state logic isn't completely stable and you feel the 0 before the 1, you can actually end up going to the wrong state. So you have to be certain that you add enough delay in your feedback path that you don't feel those next states coming around, because you can end up either in the wrong next state or you can end up with outputs glitching along the way. So it's very important that the machines operate in this very precise manner, which is your input burst arrives, you compute your next states and output variables, then those have all stabilized, and only at that point do you feed back your state variables become your present state variables. Then you let your circuit stabilize again, and then you can have another input burst. So to eliminate essential hazards, so this is called an essential hazard that happens. And the essential hazard happens if basically the two changes on the input result in a different next state or a different output value. So to eliminate essential hazards, there has to be a feedback delay requirement. We have to make sure that the fed back state variables don't come around too fast. So in other words, the feedback delay has to be greater than the difference between the max and the min delay of the logic. So you can't. So the min delays would say what's the fastest you could have logic computing, right? And the max delay is the slowest, and the difference between those two represents any potential way that something could get ahead, right? So if your next state logic, for example, was computing at min delay, but your output logic was computing at max delay, then you need to add this extra feedback delay, which balances them out. Right? So you're basically adding delay to those feedback variables to make sure that for sure they're going to be min delay plus the feedback delay is going to be greater than max delay of the entire circuit. Right? So the circuit's been given time to stabilize for sure, even if the fedback state variables are computing at min delay.
A question here.
Yeah.
So all these are done in logic, right? So in the transistor level, you don't make any modification to the transistor to the feedback loop. You done all this delay in the logic, so that's why you introduce this delay between your feedback and your actual output.
The way you create the delay in logic is you'd add like a chain of inverters.
Yes.
So you have your output, your next state logic coming around to become your input.
Mm-hmm.
So you would have to add a chain of inverters, which has a minimum delay, which is greater than this difference in delay.
But there's no specific value. It's just a ideal quantified value, which is like relatively one is bigger than the other one.
Yeah, I mean, it's not like a specific delay that must be there, but what you do need to do is you do want to make it as small as possible because it affects your cycle time.
Yeah, that's what
So what you want to do, so you do timing analysis like you do with synchronous design, but rather than computing critical path worst case delay, you also have to compute short paths, minimum delay, which I think sometimes you have to do in synchronous design because of hold time requirements. But basically you take your entire logic that you just built through your logic synthesis tech map, etc. You find your longest path, you find your shortest path. Your longest path, and then you also have to consider things like temperature and voltage and process to calculate your max and min. Right? So you would have to figure out what you think your longest delay is going to be in the worst case, and what's your fastest delay going to be in your best case. And then you take the difference of those two, and that's how much feedback delay you need. And you need to add that to your feedback path to make sure you don't have any essential hazards. Does that make sense?
Yes.
But you do want to try to make that as small as you can get away with, because it's going to be part of your cycle time, as we see. So sequential hazards can also result not only because the feedback is too fast, but also if the inputs arrive too fast. So if the environment reacts too quickly, you've got a problem too. So in fundamental mode, the environmental constraint says inputs are not allowed to change a second time. So you get an input burst. You can't get another input burst until the circuit stabilizes. So the environment has to sort of provide those input bursts in a staged manner, right? Not too fast. So to satisfy this constraint, you need a conservative separation time between inputs. So say you have A plus and B plus in a burst, they arrive. And then you compute your outputs next state and you move your state machine. The next arrivals need to come at meeting this separation time. So the separation time needs to be 2 times D max plus the feedback delay. So why 2 times D max? Because when an input burst arrives, the longest delay through your logic is D max. So it might take you D max to compute a next state variable. Then that next state variable needs to go through its feedback path. Feedback delay that we just computed was capital DF. So it's D max plus DF. And then that fedback variable hits your logic again, and it could cause changes in your logic when it hits. So then you have to compute another D max. And only at that point are you certain that you've stabilized, that the whole circuit has become quiet. Does that make sense? So that means your inputs can have to be spaced. So the separation time, 2D max plus the feedback delay. So since the 2D max term in the circuit must respond to the input change followed by a subsequent state change. That's why you need 2 D maxes. Okay? So I've told you a lot of positive things about burst mode circuits, right? One of the positive things is, the input form looks like state machines. It's very similar to synchronous design. It can use some, minor modifications to state minimization. You do need to do critical race-free state assignment. Logic synthesis, you have to remove hazards. Multi-level logic synthesis and TechMap are changed only modestly from synchronous design. So you have, and the other very nice thing is if you give me a legal burst mode state diagram with maximal set property, I can promise you we can get a circuit for you. These are all very nice properties. The one negative property is cycle time, because you have to provide your inputs in these input bursts in order to be sure that you don't have hazards, to meet all of your timing constraints. There's one additional timing constraint we have to satisfy in extended burst mode machines. So extended burst mode machines also have a setup and hold time requirement for conditional signals. So remember, conditional signals in extended burst mode, those are the signals that are being sampled by some terminating signal in your burst. So conditional signals have to stabilize a setup time before the compulsory signal transition, which samples them. And they must remain stable a hold time after the output and state change complete. So outside this window of time, the conditional signals are free to change arbitrarily. But within that window, you need to be very careful about changing those signals, because they're sampled signals, and you don't want to sample a signal that's changing. Does that make sense? It's very similar to the synchronous setup and hold time constraint. I can't believe it. We reached the end of chapter 5. So what are all the things we learned in chapter 5? So we learned how to solve binary covering problems. I'm still waiting for some binary covering problem solvers that I hope to see soon. We learned about state minimization. I'm still waiting for, I think, state minimization solutions from all of you. State assignment, critical race-free state assignment. Again, I'm waiting for a problem solution from almost all of you. Hazard-free logic synthesis, I'll be assigning today problems on hazard-free logic synthesis due next Friday. And then we've talked about extending to multiple input change. And today we talked about multi-level logic synthesis extremely briefly, just talking about how it's modified with respect to synchronous one. Technology mapping, generalized C element implementation, which we'll see again in molar circuit design, and then sequential hazards. So any lingering questions about Huffman circuits? It's all good? Okay, so you're all going to send me some things soon? How about any questions about projects? Because I'm also expecting a project proposal.
So as you mentioned, so the extended burst mode is the full process.
Right, so the extended burst mode synthesis process is probably too big for one project.
Okay, so I just need to choose one step of the process.
Yeah, ideally. So I would look at the two papers. So Kenneth Ewan wrote 2 papers on extended burst mode design. And you could read those 2 papers and see what aspect of the design process is most interesting to you. So one possibility would be to do logic synthesis, for example. You start with a burst mode state machine, and it's already had state assignment done to it. and you could do logic synthesis for that, hazard-free logic synthesis. Other options would be doing things like adding the state variables to a burst mode state machine. And I have a number of example files I could give you. So if you wanted to do the state assignment part of it. I'm not sure about state minimization, whether that's really interesting for burst mode machines per se. I would think it would probably be state assignment or logic synthesis, or it could be generalized C-element logic synthesis. There is also a paper that one of my former students wrote using an algorithm from speed-independent design we're going to learn about next to do logic synthesis that I could point you to if you decide you're interested in doing hazard-free logic synthesis. So I'd suggest picking something. I would look at Ken Yoon's papers first and read through, and you'll see a lot of similarities to stuff I presented, but see what aspect of it interests you the most. But yeah, doing all of burst mode synthesis would probably be a project and a half, at least. You have any idea what you want to do, Vikas?
Not yet.
Haven't thought about it at all?
No, that's what I was about to ask. Like, we had like 2 paper deadlines by Sunday, so can we like, can I tell you by like Monday evening or Tuesday?
It's nice that you asked. Not always asked. Yeah, especially if you can figure out how to get Harsha back to class. Is he doing all right? He said he'd been ill.
I don't know. I haven't met him.
Okay.
I'll check with him.
Yeah, I mean, I'd like to get them before spring break for sure.
Yeah.
But I also am putting out another assignment due before spring break. And I'm hoping also during spring break you can start really thinking about your project and start.
How many more assignments after the spring break?
After spring break, probably maybe 2,
So we can focus on our.
so you can focus on your project. But if people stop coming to class, then maybe 3 or 4.
I will come to.
So actually, we're at a pretty good point. There is one topic left that I think we skipped earlier, which I'm just going to go back and look at what was in that. So if you remember, we were talking about graphs and Petri nets and reachability graphs and all of this. You guys actually did, I think, pretty well on that assignment, going through all these different types of graphs. But we left a bit hanging on the end here about state assignment. And we're also going to go through how to do state exploration, a little bit more detail, finding state graphs, because that's useful for the next aspect. So I'm going to, on Tuesday, step back and talk about these STGs, because STGs, or signal transition graphs, are basically the input form that's the most favorite one for people doing speed-independent design. So a lot of the software tools that do molar circuits or speed-independent design, they use STGs as their input form, just like in Huffman design, the most common and favorite input form right now is burst mode and extended burst mode. So I'll go back and talk about STGs and state graphs on Tuesday, and then I think we'll call it a spring break, because I have to go to DC for an NSF panel, and I think this is actually a really good spot to end for the first half, and then we'll go to molar circuits after spring break and talk about that, timing analysis, verification, and you'll start working on your projects. So do you have any thoughts what you're thinking about doing? I'm just curious if you...
I was thinking about like reusing BCP. So
To solve what?
maybe like go over all your research work and pick any paper and see if I can use BCP.
So there's this
I mean,
temptation
not
that
just-
students
not just-
always get is they've implemented BCP, so now they want to use it in the project. And that's fine if it's one of the parts,
Yeah,
but just make sure it's not just like applying different problems.
Or probably use it for maybe anything related to as like a last step of logic synthesis, but yeah,
Mhm.
of course, any other things which I can implement before.
So state assignment hasn't been chosen yet. like critical race-free state assignment that has UCP. State minimization has been chosen. I have 1 or 2 people doing logic synthesis depending upon what you decide to do. There's also topics coming in the later chapters, which might be more relevant to you. Like, I mean, you're doing stuff more related to verification, stuff like that, maybe. So you might want to look at some of the later chapters to see if there's any topics that look interesting to you. Because in chapter 6, we're going to be doing logic synthesis again, but we're doing it for speed-independent circuits. And in chapter 7, we're going to talk about timing analysis. In chapter 8, we're going to talk about formal verification. So you're all free to look at those chapters and see if there's a topic in there like, yeah, so there's things like doing comparing specs to implementations, temporal logic. Have you learned about temporal logic in other courses? So temporal logic verification, stuff like that, which might be interesting to you. That's like I've mentioned before, is that one thing I hate about this doesn't all need to go onto the video. Yeah, it would be nice if there was a way to